Welcome to this explainer. Okay, today we are cracking open chapter 2 of theoretical machines, position, posture, and displacement. Listen, if you're a fresh engineering undergrad, you already know that translating physical motion into rigorous vector math can honestly feel like learning an alien language. But if you've ever wondered how the chaotic, violent movement of an engine block is somehow tamed into clean, elegant equations, well, you're in the exact right place. We're going to build this step by step. Here is our roadmap for today. First up, defining position and observers. Second, posture, beyond simple position. Third, the loop closure equation. Fourth, analyzing linkage postures. And finally, displacement, translation, and rotation. All right, let's jump right into section 1, defining position and observers. To define where absolutely anything is in space, we absolutely must have a coordinate system. Think of it kind of like dropping a pin on a GPS map. If you don't have a starting reference, those coordinates mean literally nothing. So, this requires 3 anchors: an origin for the observer, agreed upon axes for direction, and a scale to actually quantify your measurements. Without all 3 of these, any mathematical values we assign to a point are just random numbers floating in the void. Now, with our coordinate system solidly established, we can define the position of a point. And that is simply a vector stretching directly from our stationary observer at the origin right to the target point. Position inherently requires both a magnitude, how far away the point is based on our scale, and a direction based on our axes. Imagine you're standing at the base of a huge robotic arm. The position of the welding tip is just the straight line distance and angle from your eye directly to that tip. Moving on to section 2, posture, which goes beyond simple position.
Undergrads frequently confuse these 2 terms, and hey, it's a super easy trap to fall into. The crucial difference you need to remember is that position just locates a single dot in space, while posture locks down the exact location and the orientation of an entire rigid body. I mean, if you just give me the position of an engine valve, actually scratch that. Even if you give me its exact center coordinates, I still don't know if it's tilted, upside down, or perfectly aligned with the cylinder. To design a functional machine, we have to know the full posture.
So how do we do that? Well, to track a complex part, like a connecting rod, we have to literally, mentally bolt a coordinate system directly onto the moving body itself. As the machine revs up and that rod thrashes around, our bolted-on local coordinate system moves right along with it. This is what allows an outside observer to accurately measure the part's exact orientation and angle against a stationary, fixed-world frame.
Which brings us to section 3, the loop closure equation.
I know loop closure equations can look terrifying in a textbook, but this concept turns all that crazy math into a really simple logical recipe. We represent every single rigid link in a mechanism as a vector, we connect their joints end to end to form a polygon, and then we just set the entire sum to 0, because mechanical links form closed kinematic chains, right? So their individual vectors absolutely must mathematically cancel each other out when you trace a path from the ground frame through all the moving parts and right back to the ground. Let's really unpack this quote, because the stakes here are incredibly high. The polygon formed by the position difference vectors must remain closed. If this loop closure math isn't perfectly precise, your simulated machine won't just move a little bit wrong. No, the software will mathematically tear the joints apart. Or worse, your physical prototype will instantly lock up and snap. The constant lengths of these vectors are the mathematical equivalent of solid forged steel. They are literally the only thing guaranteeing your machine stays in one piece. Okay, section 4, analyzing linkage postures. Now, when we actually solve these loop closure equations, the math frequently spits out 2 completely different, perfectly valid answers. This proves that the exact same machine parts with the exact same lengths can actually be assembled into 2 completely different configurations. In a classic 4-bar linkage, we call these the open posture and the crossed posture. In a computer simulation, clicking a button to flip between them is easy. But in the physical world, to get from an open to a crossed posture, you'd actually have to unpin the joints, physically cross the heavy metal links, and completely reassemble the whole shebang. Finally, section 5, displacement, translation, and rotation. Let's make things move. It is absolutely essential to realize that displacement is not the same thing as total distance traveled. Displacement couldn't care less about the curvy, chaotic, real-world path a point takes over time. It only cares about the mathematical difference between where it started and where it finished. It's strictly the final position vector minus the initial position vector. Think about it. If a gear spins exactly 1 full rotation, its total distance traveled is the circumference, right? But its displacement, exactly 0.
But wait, what happens when our observer stops standing still on the ground and actually starts moving with the machine? This question forces us to think about relativity in engineering. The underlying kinematic math changes entirely depending on whether your point of view is permanently fixed to the laboratory floor or if you are virtually riding on top of a spinning gear.
So we pit absolute displacement against apparent displacement. Think of a standard cam and follower mechanism. From a stationary ground frame, the absolute motion of that follower might look like a wildly complex, totally unpredictable curve. But if we attach our observer directly to the moving guide, the apparent motion of that exact same part becomes incredibly simple. It's just a straight, predictable slide up and down. By cleverly shifting our observer to a moving coordinate system, we can drastically simplify our kinematic analysis. It's a real game changer.
This quote right here, this is essentially the holy grail of kinematics. Every chaotic, messy, multi-directional movement in a complex machine can be mathematically boiled down to just two fundamental things: sliding and spinning. Whether you're analyzing a 6-axis robotic arm on an assembly line or the massive deployment of an aircraft landing gear, its total displacement is always just a net translation of a specific point plus a net rotation of the body around that point. Just to clear up any lingering confusion before we wrap up, pure translation means every single molecule of a part moved the exact same distance and in the exact same direction. It's like sliding a heavy textbook straight across your desk. Rotation, however, means points further from the pivot had to travel a greater distance, like pinning the corner of that textbook and spinning it around your finger. If you draw two dots on a mechanical link and they travel completely different distances during a movement, you absolutely have rotation happening.
So I'll leave you with this provocative thought to ponder. The rigorous vector math and coordinate systems we just explored, they aren't just dry academic theory meant to torture undergrads during midterms. These equations are the absolute literal boundary between a highly functional machine and catastrophic, explosive mechanical failure. A bad mathematical constraint on paper means a broken physical machine in the real world. Think about that the next time you're trusting the linkages in your car's suspension at highway speeds. Thank you for joining me on this explainer of Chapter 2. See you next time.